operator in the cylindrical coordinate. Okay, so the starting point is the expression in Cartesian coordinates, which is given by start from this, and all we have to do is to replace the unit vectors in terms of the unit vectors in the cylindrical coordinates, for which we have already got the formula. Again, in terms based on the expression of the unit vectors in the cylindrical coordinates in terms of those in the rectilinear coordinates. We can invert them and get this. We have to express these in terms of derivatives involving d by dr, c, d by d phi, d by d z, c in the obtained field. That is obtained using the chain rule, and so we can put everything together, and then we get this important formula for the Laplacian in the cylindrical coordinate given by how the moon acts on a scalar field. That means the scalar can be a function of position as well as time. We really don't know, but here we are looking at everything only involving with respect to position, and so we have the following form. The radius of scalar is very easily obtained. We then looked at the divergence of velocity, and say of any vector field. So we take this, and then all we have to do is to understand how this kind of an operation is to be done on a vector. This would apply for any of the vector operations that we are going to consider. The crucial point, I can take any one of them and take the term involving phi, because that is what will lead to some complication, because all the unit vectors are, I mean not all the unit, two of the unit vectors in the cylindrical coordinate are dependent on phi. So we have to take that into account, right? Whereas that problem was not there in the rectilinear coordinates, right? So we have this. So as I pointed out, the way to do this is to separate out first the vector operation like this, and then carry out the derivative operation, right? So then what it will lead to here is two terms, one involving the derivative with respect to BRC, and ERC will remain, whereas BRC times the derivative of ERC with respect to phi, we've already seen that will give the unit vector E phi. Right? So we will add that. And now we know how to take the dot product of a vector with a vector, because it's an orthonormal basis set. Right? Clearly, this term, because of the fact that E phi dot ERC is 0, will cancel out, and however E phi dot itself is 1, and so we get the term BRC by RC. Okay, so that is the same idea that is used even if you take the cross product, or rather the curve of the vector field. So the idea remains the same. Again, I take the same term. So the idea remains the same. So clearly this part doesn't change at all. Only now I have to take the curve, or rather the cross product of the vectors, and again I can easily show, if you are not convinced, that for instance we note down these basic substitute ERC in terms of E1, E2 and E3 and same here. Take the cross product and you can easily verify this because we know what the operations are, how the cross product is defined for the unit vectors in the rectangular coordinate system. So that is what we get. So the cross product now is E5 dot ERC. Here would be the sort of the reverse. E5 dot ERC clearly is minus EZC. So that would give rise to minus 1 over RC dV RC by E5 times EZC. Vector will also come into play. And so then the other term involves the cross product of E5 with X. So that would be 0. That will not contribute anything. Right? So we've already done this. I'm just recapping what we did. Then we could look at the tensor product, the gradient of a vector, right? That would lead to the tensor product of two vectors. Gradient acting on a vector. This is just gradient acting on a vector. We've already seen that that would give rise to a tensor. So we discussed the idea of a unit tensor. Just there are 9 unit tensors in the rectangular coordinate system. There are also 9 unit vector tensors in the cylindrical coordinate system. Right? So now how would this act? Right? So here of course there will not be any zero terms. So if you want, I can just put this. It is done in many of the textbooks. This is also the same as a tensor product, but some books just remove this. So when you put a vector right next to another vector, it is regarded as a tensor product of the two vectors. So if I do that, so then I will get two terms. One would be 1 over RC dV RC by E5. E5, the order is very important. First, then we have ERC by RC, E5, E5. That's what we did. I just picked one operation. So you have to really look at the whole operation acting on the whole vector, right? And then figure out what are all the terms that would cancel out. That's somewhat easy to see, right? Because the crucial point you have to remember is none of the unit vectors in the cylindrical coordinates are dependent on either RC or ZC. And two of them are dependent on phi. So that if you keep in mind, by inspection you can easily see which are the terms that are going to cancel out. So if you're not sure, you just go and write each and every term and then get familiar with how to do this in an efficient and quick manner. Are there any questions? This has all been covered, yes. No, not at all. Velocity gradient tensor is not necessarily symmetric. You can again look at the symmetric and the anti-symmetric part. Construct the tensor D. That would be the symmetric part of the velocity gradient. That will discuss. In fact, the Stokes hypothesis has now to be modified because Stokes' original derivation involved only a linear transformation. He said that the form, the dependence of the stress tensor on the deformation tensor is not affected by linear transformation of the rectangular coordinates. Now we have to see that we will directly adopt the same form in the curvilinear coordinates also, which means that the proof that Stokes gave has been generalized to include all possible transformations, including non-linear or curvilinear transformation. We will not give a proof of that. But anyway, that's not yet relevant. We'll come to that later. This is merely the operations that we are looking at that involve the gradient. Of course, the relevance of that is in that we want to now write the continuity and the equation of motion, particularly for a linearly viscous fluid, which is what we have considered so far. In terms of any curvilinear coordinate system, at least any orthonormal curvilinear coordinate. So we can see that the equation of continuity will involve the divergence of rho times B. If I know how to calculate the divergence of a vector field, right, then I can easily calculate the divergence of any vector field. Right? Simply chosen as B, but wherever B appears in our formula, you can substitute rho times B, and then you will get the answer. Similarly, the equation of motion would give rise to this. In turn, for a linearly viscous fluid, this would lead to the Laplacian of the vector. Right? So we've already covered this. Now, what about the dot product of B with the gradient, velocity gradient tensor? Right? If I want to do it using the unit tensors and the unit vectors, then I would have to write this as BRC, ERC. We can do it, but it's much easier to be multiply. We do a matrix multiplication. If I want to do it the same procedure, that would apply here also. So I have already calculated the velocity gradient tensor. So it would probably have terms like dVRC by dRC, ERC, ERC. 9 terms would be there, right, for each of the unit tensors. So this will now bring into focus, right? If you now look at a particular term, for instance, let's take this. Hopefully I've written the first term at least correctly. The first term correct is what we have in the notes. Right? So, yeah, that seems to be correct. So, there is other terms. Let's now take again this. I'm doing the same thing that I've done here. Right? If I were to do that, then I will get here the no action of the Laplacian has everything taken into account. I'm really looking at the dot product of a vector with the second order tensor. Right? So that would be d phi e phi. So there's no question of derivative here. Right? dVRC by dRC, ERC, ERC. Here again, we can show that the formula I wrote down for the rectangular coordinate system, namely EI dotted with EJ, EK is equal to EI. So delta IJ EK. That will apply carry through to the cylindrical coordinates also. Again, if you want to prove it, you just have to express, for instance, let us take this. So this would again be the same, right? This is the so we take the scalars out, right? That's easily done, right? It's just a simple dot product. There's no derivative involved here. So we get, and then I get E phi dotted with ERC, ERC. Now if I argue that the same formula that I have written down for the here I equal to 1, J, I equal to 1, 2, 3, J equal to 1, 2, 3, and K equal to 1, 2, 3. This will also correspond to the rectangular coordinate system that we have worked with so far. Right? But if I argue that the same formula would now apply for the unit vectors and the unit tensors in the cylindrical coordinates, what do you think this would be? The value of this, it would be 0 because this is nothing but E phi dotted with ERC, ERC, and this is 0. So this is a direct verification of this formula. Only here I have the delta. Here I can make the same thing. I can now put a substitute 1 for RC and substitute 2 for phi. The same formula would hold good here also. So E phi dot ERC is 0. So that would be 0. So in the same way I can do all kinds of then there are 3 terms here, and there are 9 terms here. Right? So you have to take the operation of each one of them with each one of these terms. But however, because this formula holds in the cylindrical coordinates, we can simply do what we would do to calculate this quantity in the rectangular coordinate system by simply doing it like this. Simply doing this multiplication of the transpose of a vector with the tensor, just as you can easily verify. If I were to carry out a somewhat long-winded procedure, the answer would be the same as whatever it is on the other elements, right? So you can simply write those other terms. This would be phi by drc, and then this would be sec by drc, right? And then all the other terms. So I just carry out this multiplication. And I will get, so this is a 1 by 3 matrix, and I have a 3 by 3. So the net result would be a 1 by 3 matrix. So if I do this, I will get some question, some, this is 1, term 2, and term 3 along the first row. This would be the result, and I can easily identify this to be the component of d dot del p along the RC direction, this to be the component along the phi direction, and this to be the component along the ZC direction. That operation is valid, and we could do the dot product of vector with the tensor just as we did for the rectangular Cartesian coordinates. Or we can split the tensor into its unit tensor and then make use of this formula and do it. It will be identical, as we in fact saw that we in fact even to the rectangular coordinate I in fact introduced the formula first, and then later on said that the same formula would come if I were to write A in terms of the unit tensors and A the vector in terms of the unit vectors. I would get the same formula provided I adopt these rules for the dot product of the unit vector with the unit tensor. The same idea holds good. So the complication comes to the cylindrical coordinate only when we are dealing with the gradient operator. Here we are dealing with it, but that is already taken care of. At this stage, I am only looking at it as the dot product of a vector with a tensor. Right? So at that point, there is no confusion at all. It can be done just as you had done it for the rectilinear coordinate system. Are there any questions? So the formula I will write down later, but it is there in all the books. So we'll come to that when we try to write down the equation of motion in cylindrical coordinates. Now, even though we are going to look at the equation of motion only for the special case where we assume a linearly viscous fluid, it is important to know how to calculate the divergence of a tensor in the general case, right? Before getting into this is the general equation of motion. So we will now see how to evaluate, right, the divergence of a tensor in cylindrical coordinates. That's the next operation we are going to consider. There we will find this kind of a simplified approach will not work, and we have to express necessarily the tensor in terms of the unit tensors. We will see how that would work. So again, the idea is the same. I have identified the gradient operator, that remains the same. So that would be written as ERC d by drc plus d phi by rc d by d phi plus dzc d by dzc. So it's a dot product again. But what I have right hand side, on the other side is a tensor. Now we will see that we have to necessarily deal with these kinds of rules. Right? There's no escape from it, it looks like. So I have to now write all the plus, right? So this would be d phi RC, d phi RC, d phi phi, d phi phi. And then the first set of terms I consider will correspond to the first row of the tensor T, right? And then further plus E ZC RC E ZC E RC plus E ZC phi E ZC phi plus E. This is what I have. So clearly now I have to consider the operation of each one of these. So there are three operations, separate operations here. Each one is acting on the 9 terms, right? So, and then if you multiply it by page 3, I have to really consider 27 operations. And the final result will be the combination of all of these. However, again, some of them you can easily guess. Now the terms involving these two operations are going to be the simplest because they, the derivative of the unit vector, those terms with respect to both RC and ZC, those terms would be C. We are not going to contribute. So the real complication only will come from the middle term. So let's now take this and see what would happen. Right? Suppose let's say I take ERC d by ERC dotted with ERC RC. Let's take one and then I generalize the same kind of phenomenon is going to happen for the other terms as well. So if I look at this, the procedure is the same. The only difference, so I take out the operation, the vector that is there out. The vector operation here is a dot product. So the idea is the same, right? But now I'm going to differentiate a tensor. So it is actually a product of three terms, the tensor component and the two vectors that contribute to the unit tensor. Again, order is very important. So because here both are the same, so it doesn't matter. So I have this. So I get three terms, ERC, RC times the derivative of ERC with RC and then ERC. So all those terms would vanish. So what this would mean is that the only term that would contribute is the one that would involve in this. Now if we look at this, this is actually a sum of three terms. The first term would be ERC, RC times, I am not differentiating it, so the other one would involve the differentiation of ERC, ERC. Those, again, that would be two terms that would all be zero because ERC doesn't depend on RC, right? So the only term that would contribute is ERC dotted with DERC, RC by ERC, ERC, ERC. Wait a minute, this is just a scalar coefficient. It can be written as times ERC dotted with ERC is 1 and then you get ERC, so I get a component in the ERC direction, the RC direction, right, around ERC. So now can you tell me what would be the action of this on the second term? That is, I am looking at this on the second term. what would, for instance, ERC dotted with now d by drc, that's the same. ERC phi, ERC phi. What is that going to give? By inspection, right? Again, I can write down all the terms, but you can clearly see that again there is no term involving the derivative of the unit vector. The only term that would contribute is DERC phi by DRC. And that would now have a component along the phi direction. So this would simply lead to DERC phi by DRC phi. The final result has to be a vector. We know the divergence of a tensor is a vector. Okay. So clearly then, the third term in the first set of terms, right? So I can call this whole thing as 1. This would be 2. The second row, this would be 3. So if I take, for instance, 1, 3, what I will get out of 1, 3 is clearly the ERC 6 by ERC 6. So I'm getting a term in each one of the 3 directions, right? Now I can look at the action of this on each of the terms in the second row, right? What do you think will be the result? Yeah, if I come, I'm asking you what is the final result? 0, right? That is because again d by drc of E phi as well as ERC is 0. So again I'm going to get only terms involving the derivative of E phi RC with respect to RC. But what would be the coefficient of that E phi ERC? Here it would be E phi E phi, E phi EZC. Each one of those is going to be dotted with ERC. Since ERC dotted with, because each one of them will have E phi in the front. Since ERC dotted with E phi is 0, it doesn't matter what the other term is, it is going to get 0. In the same way, if I consider this with respect to each of the 3 terms here, right? Each one of them would have again ERC here behind the dot product. Each one will be with respect to EZC, which is again 0. So I can safely conclude that ERC d by drc dotted with 2 is equal to 0 and ERC d by drc dotted with 3 is also equal to 0. It's the same idea. The only difference between the terms 1 and the terms 2 and 3 is that all the terms in row 1 had ERC at front here, and since the dot product is with respect to ERC, they all gave a component in the ERC, E phi and EZC direction. However, the second and third group of terms, you would always get ERC dotted with E phi ERC, ERC dotted with E phi E phi, and then ERC dotted with E phi EZC. All of them are 0. The same way for the third is with ERC dotted with EZC ERC, ERC dotted with EZC E phi, and so on. So those terms would also be 0. You can now expect a very similar result for the operation involving ZC. And now you can tell me which group of terms would contribute, which groups would be 0. The third row would contribute, right? And the first 2 rows, the contribution coming from the operation of this, the dot product would be 0. Those terms I can easily write down by, again, by inspection. If you are not sure, you have to dot it with 1 is 0. Dotted with 2 is also 0. Dotted with 3, I will just write down the entire set of terms. Right in whatever space is available. involves simply the derivative ZC RC divided now by ZC. Now which direction that would be a component is ERC plus B by the ZC again, right? ZC phi, that would give a component in the phi direction, right? ZC dot with ZC phi. The third term would involve the derivative of the ZC, ZC, I write it here. With respect to ZC, that would be a component in the ZC direction. So we have identified 6 group of terms, right? Yeah, all these. So 6 terms we have identified. So the only terms you get from the operation of the first operation and the third operation of the entire tensor. So we have now calculated all those terms. We can now focus on what is going to happen with the operation of the phi, the term involving the derivative with respect to phi of each one of these 3 sets of terms. Right? So that is what will take us. We take a little bit more time and a little bit more care before we cancel off any terms. So let's just take and see what happens. So let's look at the first term then. E phi by RC d by d phi dotted with, right, ERC. There I can write, and because many of them are going to be zero, so here let me write down the 3 terms explicitly, and then you can see how to do this operation in general. This is a problem that we will encounter repeatedly. So first, let me carry out the derivative of the only term I calculated there, plus ERC RC, ERC by D phi, ERC plus ERC, RC, ERC, DERC by D phi. So that's what we have. So now you can clearly see that E phi dot ERC is 0. So this there won't be any contribution from this, right? I'm looking at this, so this is 0. You have to know which one is 0. So DERC by is E phi, that will clearly contribute, and this I don't even have to write this. This will be 0. So the only contribution that will come out of this is DRC, RC by RC. ERC is what that would come, right? So let us now do the next term. So you can probably, I'm trying to see what pattern you can see, because all of them have ERC in front, right? So I can easily conclude from each one of these 2 terms also, there will be no contribution from this, right? Procedure is the same, right? So this would be ERC now E phi, right? So let's take the next one. ERC. So that term is not going to contribute. Because I still have ERC at friend. This one will get, and then I get E phi. Now this term would be E phi. That again will not contribute. So the only term that would come would be ERC. Sorry, this is ERC phi. I think I should better write it. So this is fine. So this is, let's not confuse the issue. So ERC RC by RC. Is that clear to everyone? The erase is step, but you might have written it in your notebook. So it's clear that now what would happen if I have again, there will be three terms. The term involving the derivative of ERC phi with respect to phi would continue to have ERC in front, right? So that would be 0. So the next term would involve ERC by E phi. That would contribute, right? So that contribution would be ERC phi by RC, right? Then the third term would involve ERC again times dE phi by dE phi. Instead of ERC by dE phi there. So that also would vanish. So all I will get is this, and I can then safely conclude that the third term ERC Z ERC ZC. This is the ERC. It's a vector, right? So this would be E phi. And this would clearly give me ERC Z by RC Z. Right? So again, we recap the three terms that come. One will involve the derivative of the component with respect to phi. All those terms would have ERC dotted with E phi. So they would vanish because of that. The only term that would contribute is the one involving ERC by dE phi. That is actually is equal to E phi. That is going to be dotted with E phi, so that would contribute. The contribution of that would simply be the component divided by RC. Other term would be 0. And clearly, here I have ERC next, so I get a component in the ERC direction. Here I have E phi, so I get a component in E phi. Here I have EZC, so I get a component in the ZC direction. These are some of the unusual terms that come because of the dependence of the unit vectors on the coordinates, right? So let's now take the second set of terms. This is what you get from all of this. What you get from E phi by RC D by D phi dotted with just 1 is what we get. Let's now take the second set of terms. So I have not yet done. And let's look at E phi RC. Now the crucial point to note is that once you know what is the commonality between these three terms, is they all have ERC in front here, right? So that's why they all contribute to very similar looking terms. Now we come to the second set of terms. They all have E phi in front. So that is going to influence what type of terms are going to contribute. Right? So E phi ERC, if I take that, now clearly the derivative terms will contribute. So what is happening in one is likely to happen. To see the pattern, then it's easier to write it down. Right? So clearly the term involving the derivative, this is going to work for each one of the other two terms also. the second row, right? So let's write it down. So all the terms that involve the derivative of the component of the t with respect to phi are all going to have a dot product of d phi with itself. All of them are now going to contribute, not only here, but in the second term as well as the third term. Right? So, plus, now I will have d phi by d phi, that is minus drc. So that is obviously not going to contribute because all of them have to be dot product with respect to d phi here. So d phi dot and z. So that will be d phi rc times d phi by d phi, which is minus drc. And then again I have drc. And then the third term, right, would be phi rc. And again I have d phi times drc by d phi. We have to be very careful not to discard any terms just like that. So you can see that this is also now going to contribute. Right? This will contribute in the second case also, but it will not contribute in the third case because there it would turn out that dzc by d phi is 0. So let's write down what we get out of this. Right? So this would be 1 over rc erc plus this would be 0, right? Plus the third term would again contribute. It would be phi rc by rc, right? If I dot of d phi is 1, I am getting rc by d phi, which is d phi. So I am getting another component in the phi direction. So we can now write the complete phi phi d phi d phi. Right? So that would clearly 1 over rc can be taken out. So I have d phi. So the derivative d phi phi by d phi, that will have a dot product of d phi with d phi, and then it has a component in the phi direction. So that would be d phi. Now the next term, right? The next term would involve d phi by d phi. Again, just as we had here, that's not going to contribute. Right? The third term is what I am going to write, which would now involve d phi by d phi. Right? There it involved d rc by d phi. Now this would involve d phi by d phi. And so that is minus rc. Right? So that would be d phi phi minus rc. Now clearly the third set of terms, right, would, I'll just write that down and we'll be done for the day because we're running out of time. So phi z, phi zc, zc, right? Again you get the phi. Get the derivative term again. Take the rc out, 1 over rc out. So the derivative, that is going to contribute around now the zc direction. And I don't see any other terms coming because the second term would involve d phi by d phi, which is minus erc, that has to be dotted with d phi. So the third term would have a dot product of d phi with d phi, but it will equal dzc by d phi, right? Which is 0, right? This is all we will get for the action of this operation on the third term in the second row. I would expect that the action on this with respect to the third order would be even simpler. This is probably the most difficult combination of terms, right? And that would run out of time. So I will leave that as an exercise. Maybe tomorrow one of you can come to the board and explain how to calculate this, the dot product of this with respect to the third. So now still the job of collecting all the ERCs and E5s and E6s, all the terms involved together and put them all together under one form. We take that up in tomorrow's, tomorrow's